part of this material, we are going to actually look into a number set that's larger than the real number set, just as other number sets were developed. As we went along, we started out with, say, the natural numbers or the counters, and we realized 0 exists, and so we had to identify the whole numbers, and then we realized negative numbers exist, so we identified the integers. Then fractions existed, so we identified the rationals, and then we identified that irrational numbers existed. And then now, so we call them all the real numbers, and you've stayed inside the real numbers. But now we're actually going to look at stepping outside those real numbers, and such as problems we looked at before where I asked you for real number roots, where we had a negative radicand. Now we can actually solve these because we're actually going to define, and some hard sciences use these complex numbers. We're going to say that if we step outside of the real numbers, and I'll always tell you you're in complex numbers so you know that you can do a problem such as this, versus I'll ask you if it's a real number root so you know to say it's not a real number, that kind of thing. But we're going to say I exists, so I is actually the square root of -1, and we're defined as it exists. And then we actually step into a complex number system where all numbers can be written in standard form a plus bi, where this is a real number part and this is a complex number part. And so you have the real number part plus the complex number part. Now real numbers are subsets of these because b could be 0 and it would wipe that out and you just have all the real numbers. So a is any real number, b is also any real number, and the imaginary number part, that here is called the imaginary number part. And so that's the part that we're defining now that we say I does exist in the square root of -1. So if I is the square root of -1, then I squared, if you square both sides, you're going to get -1. So I squared is actually -1. So when you write these answers out, you can always write them in this form where I never has a power on it other than 1. So I'm going to list the powers here. If I have I squared, it's going to be -1. By knowing these, by just knowing that definition, I cubed now, using my exponent rules, is going to be I squared times I, which I squared is -1, and I is, we just call it I. We're not going to call it square root of -1, we're going to call it I. So we end up with -I then. I to the 4th is just going to be I squared times I squared with your exponent rules. -1 times -1, which is 1. The cool thing is, there's not a whole lot to remember here because they all repeat themselves. I is I squared is -1 always. I cubed is I to the 4th is 1. It repeats now every 4th. So multiples of 4 always end up being 1. And that's the main thing to notice. So I to the 5th is just going to be I to the 4th times I. So you just get I. It goes back to the original. I to the 6th, I to the 4th times I squared. So you just end up with 1 times I squared, which is -1. And then same thing with the I to the 7th. Same thing with I to the 8th. You end up back at 1. So any multiple of 4 is 1. I use that to my advantage. So when I'm looking at this, I could ask you any power I to the 51 is actually just going to equal, using my exponent rules, I to the 48, closest multiple of 4, times I to the 3rd. Well, I to the 48 is just 1, guaranteed, times I to the 3rd. Well, I know I to the 3rd is -I. So my final answer is just going to be, I'll put it underneath, -I. So you can take any I to any power and write it as, at most, having an I to the first power. You'll never have I to any higher powers than 1. And so we'll use that when we're writing things in the standard form. I to the 16 is a multiple of 4. That's just 1. I'm done that fast. And so that's the power stuff. Let's look at ones that are, I asked you to simplify a negative radicand, but now I'm saying you simplify these following complex numbers. I'm telling you the complex numbers, so the negative underneath the square root is really, it does exist, it's an I. So I always say is pull your I out. You see a negative underneath that square root, pull the I out, becomes positive. So, but really what's happening here is this is really -1 times square root of 100. And actually I'll probably write it this way to keep it in standard form. It doesn't matter which way you do it, but the square root of 100 times the square root of -1. You can separate those into 2 different radicals if you wanted to. You wouldn't have to show that though. I just say pull your I out. You can even write the I in front. Don't write it underneath the root symbol, but the standard form really always says put it in back. Square root of 100 is 10, and then square root of -1 is I. So this would just be 10I. And that's your answer. There's nothing left underneath the roots. This one, it's not a perfect square number, but I can pull my I out right away if I wanted to. And then this is really 4 times 10. I'm going to take the I and stick it in the back. Not underneath the root symbol, it's out back. A plus bi is the standard form. Square root of 4 is 2 root 10I would be the complex number simplified form of that. So you'll see problems like that, problems with your powers, and they'll always end up being the answer of I, -1, -I, or 1, guaranteed on any single one of those power ones. These you simplify this way, just see a negative underneath the root symbol, just pull your I out, simplify the rest of it the same way you've always done with the real numbers. And then I can look at just some standard where you have a real number part and a complex number part and apply operations to these things. So I could add these numbers. So I just picked a couple numbers and just made them up. 1 minus 2I is a complex number in standard form. And I want to add that to 4 plus 3I. The cool thing when you write this, you want it in a complex, standard complex number form. They're the same thing as like if you had an x or something, combining your like terms, right? You're just adding these, combine your like terms. You get 5. You have a negative 2i's plus 3i's. It's going to be plus 1i. That's adding them. Not so bad at all, right? What if we subtract these things? So let's subtract them. 1 minus 2i minus 4 plus 3i, just like you've done in earlier algebra classes. Same deal, just distribute your negative through and -1 through, or change the sign of all and add. So you end up with 1 minus 2i minus 4 minus 3i. Combine your like terms, write it in standard form, the real number part first. So I should get -3 minus 5i. And that's that answer if I was to subtract those. Now let's multiply and divide them. The dividing is probably the trickiest, but they're not too bad. The multiply is a little bit easier than that, but the dividing is probably the trickiest. So let's take these same two numbers and let's try multiplying them. It's just distributive property again, like you would with any basic algebra ones, but your final answer, you can't have an I to any other power than 1, right? So you can do some replacement on this. And you'll see what I mean by that. I'm just going to distribute my 1 through to everything, and then my -2i through to everything. Combine my like terms, simplify it down to standard form. So I'm going to get 4 plus 3i and -8i. Let's see, -8i minus 6i squared. That squared, though, I squared is actually -1 because of our I is I, or square root of -1. So when you square it, you get, so you just replace that with a -1. So when we go to do this, I'm going to combine my like terms. I have 4 minus 5i. And then this is going to be minus 6 times a -1. So whenever you see the I squared, just replace it with -1. You'll end up with 4 minus 5i plus 6. Combine your like terms, because negative times negative. I have 10 minus 5i. And so that's how you'll work through those, and I'm writing it in standard A plus bi form. The very last example of the chapter of the material we're going to cover is taking this complex number, say, and dividing them. And so I'm going to use the conjugate concept to help me simplify this. Conjugates wipe out middle terms. We know when we get an I square, it becomes -1. That means we're not going to have an I left in the denominator. So I'm actually going to use that to my advantage and go, cool, well, this is just going to be 4 minus 3i. I'll multiply the bottom by. Same deal to the top then. 4 minus 3i, keep it an equivalent expression. And now I'm going to combine these, doing distributive property all the way through. So the top I should get 4 minus 3i, and then minus 8i, and then plus 6i squared. And then on the bottom, when I multiply these, I'm going to get 16 minus 12i plus 12i. See, the middle terms are going to wipe out. And then minus 9i squared. And now the cool thing is at the bottom, these middle terms are going to be gone. And I squared becomes -1. All it does is just changes that sign. So you just get a number down there. And then up on top, same deal. I'm going to replace this with a -1. And so that's just going to make that a minus. So when I have 4 minus 6, I should end up with -2. Minus 3i minus 8i is going to be minus 11i. On the bottom, I have 16 plus 9 is what's going to end up being, so it's 25. But if I wanted to write that in standard form, I could just individually divide that into each. If there was any reducing to do, you would do so. But I should have negative 2 over 25 minus 11 over 25i. That's writing it in A plus BI form, and it's in standard form. So that's the end of this material. And so we look into complex numbers, and that's it.